So I'm going to speak about how AWS operates Kubernetes workloads at scale. My name is Jyoti Mahapatra, and I'm a software engineer in the Elastic Kubernetes service team. This session will briefly introduce EKS. Barry has done that already. And we're looking under the hoods of what goes on behind the architecture. What is the scale of the EKS fleet? How does EKS ensure highly available clusters at all times? What is the security posture? How does EKS manage observability, operations, and reliability? Brief introduction. EKS is a managed service. It is Kubernetes upstream confirmant. It's a managed experience, reliable, secure, and it makes Kubernetes operations, administration, and management very simple. Let's open up the hood. So EKS is set up in a single tenant architecture. Every cluster is isolated from every other cluster. The personas here in this picture are a cluster admin and a user. The cluster admin here created two clusters. They're both isolated. The data is isolated. Nothing interacts with each other. The user one on the right is using tools like kubectl to interact with the cluster. Every cluster has a isolated endpoint to interact. It is based on a network load balancer. The user performs kubectl commands, gets stuff done. In the diagram below, there's an automated workload. There's a kubelet that is hosted on the automated workload, and it is interacting with the cluster, again, through the NLB endpoint, and gets its work done. The important aspect to observe is the shared responsibility model between EKS and customers. EKS is responsible for maintaining the highly available clusters at all times. It scales up and down based on the load, and customers are responsible for maintaining their own part of the infra. A lot goes on in creating the infra. VPCs, virtual private clouds, security groups, IAM roles, and many more. It's a big thing to manage. Customers are responsible to do that, and they're responsible for running the workloads and making sure the workloads are available at all times. They could be running an Nginx or any other tools that they want, and it could scale up and down. It could put immense pressure on the control plane to get the work done. During those times, EKS is responsible for making sure the clusters is available to bear the load. If the scale doubles, EKS is responsible for making sure we scale the cluster up in no time proactively and keep the workload going. Let's look at what the parts consist of. So every EKS cluster is hosted in an AWS Virtual Private Cloud, VPC. Each such cluster has two ASGs, auto-scaling groups inside it. One of the auto-scaling group is the Kubernetes control plane, which is the brains of the cluster. It hosts the compute, which runs all the processes. On the left of the diagram, there's kubeAPI server, scheduler, controller, certificate controller, and many other things or managed things that EKS runs on this cluster. The second auto-scaling group is the etcd. It is where the data resides in the cluster. It has 3 AWS EC2 instances behind it because it's a quorum-based system. The Kubernetes control plane has 2 EC2 instances behind it at all times, at least. And all of these instances are spread out across availability zones so that whenever a zonal outage hits or something bad happens during deployment, not all the instances are lost at one go. Let's look at the communication model in EKS. In this diagram, there's a user and there's an automated workload, kubelet, interacting with the cluster through a network load balancer. That's the interface with the customers. But when customers send a request through the network load balancer, the request hits the primary interface on the Kubernetes control plane instances. Here, represented as ETH0. The request comes in and hits the load balancer. The load balancer has the 2 instances as the target groups. Since they are the target groups, load balancer is responsible for load balancing them across the 2 instances, and the request comes in and goes back. I'll be talking about the ETH1 in later slides. The next lifecycle event in the lifecycle of a request is how does the data come through? The request comes at the load balancer, hits the API server, and then the request goes on to fetch the data, which happens to be in etcd. Here, EKS uses because of use of HCD client, a gRPC model from interacting for Kubernetes control plane to the HCD. HCD ASG or instances do not use a load balancer. They all have static endpoints. EKS uses the concept of autosync to load balance and be aware of what the endpoints are available. Since there's no load balancer involved anymore, the control plane has to have a mechanism to find the membership of the 3 instances of the HCD cluster and be aware of members getting added or members getting removed and keep load balancing between them. Let's move on to the next one. This is a bit complicated, but this is the gist of how we bridge the gap between EKS clusters being in AWS hosted accounts and VPCs, and customers' workloads being in customer accounts and different siders. Let's look at the right part of the picture. In this, there's a kubelet running, and the pods and workloads on the kubelet are interacting with the API server using the Kubernetes service endpoints. There's a service in the default namespace called Kubernetes, and it has 2 IP addresses assigned to it. These 2 IP addresses seem to be in customer siders. They are actually 2 ENIs that EKS has created in customer siders when the cluster got created. When requests go through the Kubernetes service, they seem to be going to the customer account, but then they're actually attached, these ENIs are actually attached to the real Kubernetes control plane instances. So when you're hitting the endpoint to the ENI, you're actually getting into the Kubernetes control plane and getting the stuff done and get the response back. The interesting fact here is the ETH1. The ENIs are attached to the secondary interface on the Kubernetes control plane. So traffic from NLB goes through ETH0, traffic from secondary interfaces goes through ENIs go through the secondary interface called ETH1. The second part on the left is a user performing exec, logs, or proxy into the API server. This hit the NLB endpoint, go to the API server through primary interface, and try to proxy into the customer sider. But the Kubernetes control plane is not aware of how does it bridge between the AWS VPC and customer VPC. In this case, EKS maintains traffic rules, where API server, when it tries to connect to customer siders, the traffic goes to the Linux box into the secondary interface, and because it's attached to the ENIs, hits right into the pods. Okay, that was a brief introduction of all the parts that make up the EKS, the networking model. Now, EKS developers are writing software every day. How do they make sure that this software is reliable, does not have bugs, is doing all the right things? For that matter, let's look at a scale of EKS. EKS hosts anywhere more than hundreds of thousands of clusters. And every cluster has 2 control plane instances and 3 HCD instances. So we anywhere maintain between 1.5 to 2 million instances at any point in time. Deploying software on one instance and scaling it out to 2 million, you can imagine, it could take a huge amount of time. And anytime things go wrong, rollbacks would take that long, which would be not acceptable. Let's take the life cycle of the function. The function gets deployed to testing environments first. We call them beta and gamma. Tests are run in the beta and gamma environments, and these tests emit signals. The clusters emit signals. There are mechanisms in EKS to look for the signals, and when these signals look good, the deployment proceeds. If things go bad in beta, which is the scratch environment of developers, things are rolled back, looked at, and refixed. This deployment model goes through to the next environment called gamma, which is relatively more stable. More tests are run there to make sure that things are good before going to prod. When in prod, there are so many regions, above 20 at least, and deployment to each such region is staggered. Not one region is deployed at any point in time. That's where the concept of cellular deployment comes through. Cellular deployment is a very typical AWS deployment pattern, where we scope in a certain set of resources and make sure to deploy them to them at one time. If that fails, only that certain set of resources are impacted. The blast radius is not all of clusters. In this diagram, again, in the below part, represented the cells. Each cell could have cluster 1 through n, 1 through n. Whenever the deployment goes through, it hits one such cell, gets deployed, and we follow a pattern known as geometric progression deployment, in which case we deploy to one cell first, things look good, deploy to 2 cells, things look good, and then they deploy to 4, 8, and it goes on exponentially. At any point in time, if the signals don't look good, we stop there and roll everything back, which means the software gets deployed to one cell or 1,000, 2,000 clusters. Henceforth, the factor goes into 4,000, 6,000, 8,000, and so on. Now, deploying software is one thing, but how do we make sure that this software is actually bug-free? There's no problems. For that matter, EKS runs a barrage of tests. Every time, as part of the writing code, there are unit tests, integration tests that goes on with the code, but after deployment also, EKS runs a battery of tests. Those tests are called like Canary tests, load tests, integration tests, upgrade tests, conformance tests, and many more. When software is deployed to beta, gamma, and prod, all of things are repeated. A Lambda controller kicks in and runs the tests and puts the signals into a DynamoDB table somewhere. We use appconfig, and whenever the test signals look good, the software is already deployed, we activate it. This helps because activation and deactivation is easy, and deploying software takes time. Whenever we find that something bad happened, we just deactivate the software quickly. One of the interesting aspects is the use of Canary tests. When the developers write tests, they're looking at the server side, mostly. And that puts a bias that what we're writing and what we're seeing is the real thing, but it's not real. What customers are facing is actually the real thing. So Canary represents our customers. Every developer, when they write tests, they also write a Canary test, which runs workloads like the customer should do. It creates clusters, it shuts down nodes, does some chaos testing, and a bunch of other things. With such a setup, we make sure that our customer experience stays where it should be. For example, latency. We have tests which make sure that a cluster creation cannot be more than X minutes. Similarly, when we have long-running and short-running canaries. Short-running canaries create a cluster, get stuff done, delete it. Long-running canaries work as a soak test. We keep the cluster running, run the workload, and make sure that a cluster keeps running for days and days and months. And if it's not, if it's a workload starts failing, it represents that something is wrong, which is so subtle that we cannot find it in the unit test or integration test, but now we have to go look. It's Kubernetes upstream conformant, so every build goes through a conformance test too. Let's move on to the next one. The next part is how EKS ensures high availability. During the deployment sequence, we are using EC2 instances, which means the EC2 instances are going to be replaced. When they are going to get replaced, there are going to be disruption. So EKS is responsible for making sure there is absolutely no disruption to traffic. We achieve that on the Kubernetes control plane by using a blue-green style deployment. On the sequence 1 here, it's statically stable. There's an NLB, and the requests are going through to the Kubernetes control plane 2 instances. NLB using the health-Z signal from the instances to make sure it's directing traffic correctly, and the ASG and EC2 are making foundational checks like networking, storage, and many other things at Linux layer to make sure the hosts are healthy. This is statically stable. Move on to the next diagram. This is where EKS is trying to roll out new software. During this process, 2 new instances are spinned up in different availability zones to maintain high availability. At the same time, NLB is aware that 2 new hosts came up. It starts directing traffic based on the health-Z signal. If health-Z is good, traffic goes through. And we are now using 4 instances to serve traffic. EC2, at the same time, is making sure that foundational Linux health checks and the host health checks are going through too. If all of it looks good for a certain period of time, then there's a background controller which is orchestrating this which understands that and kills the 2 instances on diagram 3. And new software has been rolled out without disruption. If anything goes bad in this sequence, at that time, the software version is deactivated, the 2 new instances are killed because they're not looking good, the signals are not good, and 2 old instances were never terminated. That means cluster never saw a disruption. This style is useful for a stateful workload, like Kubernetes control plane. But how about etcd? Etcd is quorum-based. We cannot delete or terminate more than 1 instance at any point in time, otherwise the quorum will be lost. For such cases, it is very nuanced and orchestrated very slowly. 1 instance is terminated at 1 point in time, and until that instance comes back up, no other instance can be terminated. This is guided through an ASG configuration called max healthy host count, which stays at 100% at all times. In this sequence, there's a daemon running on all etcd hosts, which are also doing peer health checks. There's no load balancer here, so somebody has to make sure that everything in the cluster is healthy. That's kind of a gossip protocol-based system, and they're health checking each other, each peer, and if a peer looks bad, then they terminate each other. And also, the ASG is looking at the EC2 foundational health checks, and the new instance comes into the service, joins the cluster. If it goes through, then all is good. The process repeats 3 times, and 3 nodes are replaced. If something goes bad in this sequence, at that time, the software version is again deactivated. The new instance, which never joined the etcd cluster because it was bad, is terminated. Old cluster bumps back. Old node comes back. With the old version of software, things go back to normal. So that was all about deployment and high availability. Let's talk about security posture. Being a managed service, customers rely on EKS for making sure that the control plane is always stays fixed. It does not have any, so CVE stands for common vulnerabilities and exposures. Any vulnerabilities are not there in control plane. The shared responsibility model kicks in again. EKS is responsible for making sure there are no CVEs on the control plane, and customers are responsible for making sure they're keeping the worker nodes updated, the kubelet updated, and kubeproxy coordinates, and making sure these things are updated. EKS delivery model, the one I explained, does not allow for quick rollouts. Every vulnerability comes with an embargo period, 10 days, 15 days, when the vulnerability will be exposed and made public. EKS has to make sure that by the time it is made public, all clusters globally have the fixes rolled out. For that matter, EKS performs a in-place upgrade. Imagine that a CVE is made known in API server. At that time, EKS knows about it, creates a build, an image, and rolls it out. At that time, we use a mechanism from AWS called Systems Manager, SSM, to write scripts which do in-place upgrade of the processes. API server is running on 2 instances, and we create new processes on those 2 instances and terminate the old ones. So the time taken for the whole host or the time needed to test everything together is not needed anymore. This was about CVEs in the processes, in API server, authenticator, or anything as running as a process on the host. But what about the hosts themselves? EKS runs the Amazon Linux 2 as the base operating system, and that could have its own set of CVEs from time to time. EKS scans and makes sure that it is aware of all the Linux level CVEs from time to time, and works with the AL2 team, gets those new armies, creates new manifests or software versions that can be rolled out, and rolls them out very frequently with an SLA. So any point in time you look at a Linux host, it's always fixed. Next part is the real life, the operations. The EKS clusters are alive, and customers are using these clusters for their operations and their workloads at every time. As EKS developers, we are responsible for making sure that these clusters stay alive and available at all times. For that matter, we use metrics and logs from all the clusters, and anytime there's a problem, we get alarmed and paged. Every EKS cluster is important to us. So whenever there's a breach in high availability of any other cluster, someone will get paged and they will look at what happened to this cluster. But not everything appears as a high availability breach. Some things appear as nuances, 5x excess increases or 4x excess increases, very nuanced things that can show up in a pattern, latency increases, for example. For that matter, EKS is accumulating all the metrics in CloudWatch accounts in each of the cells that I described before. They stay there, including the logs. And out of this, EKS is running a regional controller which scrapes the cellular level metrics and creates a regional dashboard. This is the metadata level information which doesn't tell which cluster is exactly facing what, but a pattern which is observed every Monday in an ops meeting. EKS has a strong culture of observability, and every team is responsible for looking at trends and graphs every Monday and making sure they're consistent. There's no breach, nothing bad is happening. That allows EKS to engage the leadership as well. Leadership is always in those calls and listening to developers' observations. Anything that breaches or anything that looks suspicious is funded and worked upon. Anytime any problems are found, somebody has to go debug what's going on. For that matter, we use logs. These logs are only allowed on a need-to-know basis to developers for debugging, and developers can go to CloudWatch in every cell to figure more about the cluster and what it's facing. Let's move on to reliability. Upstream Kubernetes maintains 3 Kubernetes versions at any point in time, and EKS maintains 4 or 5 based on the lifecycle deprecation. Performance and reliability fixes are happening upstream at every time. Not all of them are making their way into the older versions. EKS is looking or on a lookout for such fixes and backports them to the older EKS supported versions. That means customers are getting reliability fixes which are happening in new versions, in EKS supported versions as well. The shared responsive model kicks in again. EKS is updating the control plane, but what about kubelet, kubeproxy, and all the other components? Customers are responsible for backporting if they need any performance fixes or moving on to new versions. Now, I spoke about patches. Some of the patches are unique, which makes EKS a little bit distinct from upstream, and some of the patches are just upstream patches. Let's talk about some of the uniqueness in EKS. The upstream in 121 Kubernetes version moved to a forever token, service account token to bound service account token. So customers' service account tokens cannot be forever anymore. They have to have an expiry. The upstream have put an expiry of 1 year for now for allowing migration. EKS security posture does not allow that. EKS service account tokens are only valid for 3 months. When this happened, a lot of customers said that they can't move to the new service account token model right away. And the biggest factor there was FluentD and FluentBit. They didn't have the fixes which took care of the JOT token expiry. So EKS worked with the community members in FluentD and FluentBit and made contributions to make sure that the customers have the right fixes to upgrade a cluster to 121. The second one here is allow list cider. When customers perform proxy, exec, or logs from the API server, that has a potential of breaking the cluster's boundary and exiting into the internet if the malicious actor could change the pod IP. To prevent that, EKS has a patch which does not allow any network traffic to exit the hosts beyond the customer CIDRs. So a webhook or a proxy request to a pod cannot go out if it is not in the CIDR block of the worker nodes. The third one here is lease object isolation from webhooks. Customers can install any kind of webhooks on the clusters, and these webhooks can cause the lease objects to fail. When that happens, there'll be kube scheduler and controller managers unhealthiness. To prevent that, EKS has a patch which prevents lease objects from being subjected to webhooks. Fourth one here is HTTP pagination. When customers perform unintentionally unpaginated calls to get resources which have like 1 million, 2 million count, then HDD could get into an situation. HDD memory is limited, and when you load everything into the memory for 1 million objects, it will one at a time, causing quorum loss. EKS has a patch which forces pagination from API server to HDD to prevent data durability. These are some of the patches, but EKS is constantly working with the upstream to create kits for this. These are all in Kubernetes issues, and EKS is working on making sure these are made upstream. This is the last one, zonal outages. EKS is not immune to outages. Outages happen in EC2 land all the time. And when that happens, EKS makes sure that anytime an outage happens, instances get terminated without notice, clusters don't get disrupted. They are still serving traffic. For example, when an outage happens, an HDD host could be gone. EKS makes sure that the cluster is not being upgraded at that time. One of the control plane instances could be gone. EKS makes sure that he can scale the cluster up proactively whenever needed so that even one instance can serve all the traffic. Last one is vertical autoscaling. When customers put a lot of load on Kubernetes control plane, the control plane can get into a situation of pressure, CPU, memory, and many other things. EKS has a service called vertical autoscaling service, which knows the heuristics and proactively scales the cluster. Some of the heuristics are just in time, that CPU increased, memory increased, so replace the nodes from, let's say, M5 large to M5 2x large, or any of that ladder combinations. Similar with HCD. We also do proactive scaling, which means whenever a node reaches, or a cluster reaches 400 nodes, for example, just putting a number there, we proactively scale the cluster. If a cluster reaches, let's say, X thousand pods, it's going to put a lot of pressure, so we proactively scale the cluster as well. So we do all of this to make sure that the cluster stays healthy, reliable, and active at all times. There's a lot, so thank you. Again, my name is Jyoti Mahapatra. You can find me here hanging out in the hallway, or I'll be in the AWS booth throughout the KubeCon. So hit me up with questions later. Thank you.